Welcome to this video about algebraic restriction codes and their applications. My name is Jesko and this is joint work with Divesh, Nico, Mohammad, Giulio and Maciej. First I'm going to introduce algebraic restriction codes, then I will show you how we use them inside of cryptography, and finally I'm going to show you a construction of an algebraic restriction code. Imagine you have a device where on input x0 and x1, where both of these are vectors, this device is supposed to publish a times x0 plus x1, where a is a scalar. This device, however, can misbehave and instead of multiplying the scalar a, multiply an arbitrary matrix a to x0 and publish the result. And this is what we want to stop with algebraic restriction codes. So what we do instead is use some randomness R to encode x0 and x1 into x0 hat and x1 hat. Then we send this off to the device. The device will publish a x0 hat plus x1 hat. Now we also publish R, and the public can reconstruct a x0 plus x1 from these two values. If, however, the device misbehaves now and publishes a times x0 hat plus x1 hat, the public cannot reconstruct small a times x0 plus x1 or any other value dependent on x0 or x1. Now, that was an example. Now I'm going to go into the definition of algebraic restriction codes. We have two sets of functions. F, which is a subset of G. F contains all the functions that the device is supposed to be able to evaluate. G, however, contains all the functions that the device can actually evaluate. An algebraic restriction code has two algorithms. An encoding algorithm, which uses some randomness to encode its input x into x hat. Then a function from either of those two sets can be evaluated on the encoded input. This results in an encoded output. The encoded output can then, using the same randomness as before, be decoded again. Now, this is correct if for every function in f, the decoded value is the same as if you evaluated the function on the original input. However, if you use a function outside of f but inside of g, then the output of the decoded value should be uniformly random. Now I'm going to show you how we use algebraic restriction codes in cryptography, namely in building an oblivious transfer protocol. Oblivious transfer is a two-party protocol between a receiver and a sender. The receiver contributes a choice bit B, and the sender contributes two strings M0 and M1. And at the end of the protocol, the receiver learns MB. However, she does not learn M1 minus B, and the sender does not learn B. Oblivious transfer is interesting as it is sufficient to build arbitrary, secure, multi-party computation protocols. Using algebraic restriction codes, we can build a RAID 1 statistically sender-private two-message oblivious transfer protocol without any setup assumptions, all just under the decisional Diffie-Hellman assumption. To understand the oblivious transfer protocol, I'm first going to explain to you linearly homomorphic encryption. A linearly homomorphic encryption is a special kind of public key encryption. A public key encryption scheme has two keys, a public key PK and a secret key SK. The public key here is used to encrypt a message M into a ciphertext. Then The secret key SK can be used to retrieve the message back from the ciphertext. In the scheme I'm talking about currently, the messages are n by n matrices over the integers modulo p. A linearly homomorphic encryption scheme additionally has the ability to modify the ciphertext using the vectors a and b, such that if you modify it, you get a new ciphertext C prime, and if you decrypt the new ciphertext C prime using the secret key again, you get the original plaintext M multiplied by A plus B. A and B here are the vectors from this evaluation procedure. Now I'll show you that a linearly homomorphic encryption scheme already is almost an oblivious transfer protocol. The receiver simply multiplies its choice bit B by an identity matrix of size n and then encrypts it inside of the linearly homomorphic encryption scheme. It sends the ciphertext together with the public key to the sender. The sender then evaluates a function which multiplies m1 minus m0 to b and adds m0. This is evaluated on the ciphertext and yields a new ciphertext C prime. This new ciphertext C prime is then sent to the receiver, who can simply decrypt it and retrieve MB. The main problem with this setup, however, is that if the receiver wants to cheat, she can simply encrypt an arbitrary matrix A and send it to the sender. If the sender then goes ahead and does the same thing as before, multiplying by m1 minus m0 and adding m0, the receiver can learn the result of this function, which she is not supposed to learn. This already sounds a lot like the problem I've outlined earlier. An adversary can multiply by an arbitrary matrix instead of just a scalar. Now, we can stop this by using algebraic restriction codes. Now we simply modify the protocol by first encoding m0 and m1 to m0 hat and m1 hat. Then, if the receiver encrypts the matrix B times identity matrix, and the evaluator evaluates the function multiplying by m1 hat minus m0 and adding m0, the receiver learns mb hat and can decode it using the randomness R to mb. If, however, the receiver encrypts a matrix which is not a scaled unit matrix, the receiver will only learn A times m1 hat minus m0 hat plus m0. As we know from the definition of algebraic restriction codes, this will result in a uniformly random value. Finally, I want to take a look at our explicit constructions of algebraic restriction codes. The first one is the one that we've already looked at, where the allowed set of functions simply scale x0 by a scalar and add x1. But the possible functions are the functions where x0 is multiplied by an arbitrary matrix and x1 is added. In our second construction, the allowed functions take the input and multiply it by an arbitrary matrix. However, the functions which are possible to apply are actually all compressing functions. At this point, I want to note that compressing in a sense is necessary, because if the set of evaluatable functions contains injective functions, then they are invertible and the notion of algebraic restriction codes are impossible. Now I quickly want to go over the first construction. In this construction we get two inputs, x0 and x1, each of length n. What we do is we sample a uniformly random matrix of size n times m, where m is bigger than n. Then we sample x0 hat and x1 hat such that r times x0 hat is x0 and r times x1 hat is x1. Then we can simply evaluate the possible functions which multiply an arbitrary matrix A to x0 hat and add x1 hat and decode by multiplying R again. You should know that if A is a scaled unit matrix, then R times A times unit matrix times x0 hat plus x1 hat. This R distributes into these and can be swapped around with this scalar. This means that it is equal to this expression, and because how x0 hat and x1 hat are defined, this means that it results in A times x0 plus x1. The basic reason why this doesn't work if A is not a scaled unit matrix is that A and R do not commute. The second construction follows a similar philosophy, however it needs a strengthened version of the XOR lemma. If you want more details about the other algebraic restriction code construction, the choice of linearly homomorphic encryption scheme, how we achieve this rate 1, how we are able to limit B to 0 and 1 instead of the entire integers modulo P, and a more detailed proof of the first algebraic restriction code, please check out our paper. And these are the references.